So, good morning, all the participants, and we are happy to invite the guest speaker today, Dr. Santosh Kumar Guguloto. We welcome all of you for this online short-term training program, Day 3. I am privileged to introduce our guest speaker today. So, he is currently working as an assistant professor in the Department of Mechanical Engineering, National Institute of Technology, Andhra Pradesh, West Godavari. Before that, he worked as an assistant professor in the Department of Mechanical Engineering, NIT Hamirpur, and various other institutions like MLR Institute of Technology, Hyderabad, Geetham University, and also at ICFI. He also worked as a teaching assistant for a period of 2 years in the Department of Mechanical Engineering at IIT Madras, and he served various institutional and departmental roles as assistant warden, DASA and study in India Nodal Officer, National Faculty in Charge Training and Placement, member medal to Best All-Rounder, member DSC, convener UG Curriculum and Course Scheme. He has about 32 conference and journal publications as a token of his interest in the areas of cavitation, heat transfer in space applications, IC engines, energy efficient thermal systems, computational fluid dynamics, microscale flows, and biological application of ultrasound. He has completed his PhD from in 2000, in thermal engineering, and he did his MTech, as I already mentioned, from IIT Madras. And currently he is supervising multiple faculty all around the different private colleges, and also he is currently supervising many PhDs and MTechs thesis. And most important to recognize his awards and achievements. So he has done his invited lectures as a keynote speaker in the 7th International Conference at China, and is also invited as an expert speaker for the online 1-week short-term training program. He has organized multiple faculty development programs and also workshops such as like this, and FDPs and training sessions. So he has published 3 book chapters, and then he has got various administrative positions and also academic level as well as at the department level and institute level. So to mention few of the honors, awards he has. So he is an advisory member of Union Public Service Commission in the examination reforms, and he's a reviewer of Fuel, a very famous SCI journal. So he's a reviewer of it. And he is selected for the Rashtriya Gaurav Award in 2018. And not to mention, last but not the least, his GATE score is very, very tremendous. In 2008, he has got All India 37 rank. So he stood 3rd position in his undergraduation. So there are plenty of things that we are happy to introduce a speaker today, and we welcome you for the session, sir. Thank you.
Thanks a lot, Dr. Vishwanath, sir.
Thank you, sir.
So can I share the screen?
Yes, we have given you co-host. You can share your screen, sir.
Yeah. So is my screen visible, sir?
Perfectly fine, sir. Yes.
Fine. Okay. Okay. So can I start?
Yes, please.
Okay, fine, sir. So first of all, I would like to thank the management of Anurag University, and especially the coordinators for this international short-term training program on recent advancements in fuel cells and hydrogen storage, which is jointly organized by Department of Mechanical Engineering, Anurag University, Hyderabad, in collaboration with the Center for New Energy Transition Research, Federation University, Australia. First of all, I would like to congratulate the coordinators for collaborating with the foreign institute, like in such a small span, deemed university like Anurag University, they are conducting such a good programs. So special mention to Dr. P. Vishwanath, Associate Professor, Dr. Jibtesh Kumar Panda, Associate Professor from Anurag University, who is my very good friend, and Dr. Surbhi Sharma, Associate Professor from Federation University. So, congratulations to all of you for conducting such a good program, and which is very, very important topic, fuel cell, which is also new to me. I am also learning in this particular area. And I'm very happy to deliver a lecture on this thermodynamics of fuel cell. So myself, Dr. G. Santosh Kumar, at present I'm working as an assistant professor in the Department of Mechanical Engineering at NIT Andhra Pradesh. So coming to the thermodynamics of fuel cell. So in this particular lecture, I will be focusing about the introduction of what is meant by fuel cell, construction of the fuel cell, working of the fuel cell, features of the fuel cell, types of the fuel cell, followed by the advantages and disadvantages, and what are the different reactions we are going to consider in different fuel cells, followed by the materials used, various losses, what is meant by low temperature fuel cells as well as the high temperature fuel cells. So basically some of the topics or the concepts we have included in my presentation is my PhD scholar's work, which he is doing on the fuel cells as of now. So I will try to introduce those concepts also here. So coming to the introduction, as itself we are clearly mentioning that we are talking about the thermodynamics. Basically, thermodynamics is nothing but a branch of science which is dealing about the energy. And in thermodynamics, we are going to talk about the conversion of energy from one form into the in thermodynamics, we are going to talk about what the conversion of energy from one form into the other form. And here, whatever the equations which we are going to consider, they are essential for understanding the fuel cell performance. And basically, fuel cells here are nothing but the electrochemical devices which are going to convert the chemical energy into work in the form of the electrical energy as well as the heat. As we know that whenever we talk about the thermodynamics, basically in thermodynamics, we are going to talk about the conversion of heat into work or else from work into heat. And also we know that heat is considered as the disorganized form of energy or low gradable energy, whereas work is considered as the high gradable energy, which can also be considered as an organized form of energy. So the aim of the thermodynamics is to convert the disorganized form of energy into organized form of energy in an efficient manner, which means in a best possible way, we are trying to convert one form of energy into the other form. So coming to the fuel cells, we are talking about the electrochemical devices which are going to convert the chemical energy into work in the form of the electrical work, which we are talking about electrical energy, and some amount of heat is also going to be dissipated to the surroundings. And whatever may be the thermodynamic system which we are going to consider, it needs to obey the different laws of thermodynamics. And especially here, when we talk about the laws of thermodynamics here, in case of fuel cells, even though there are different laws of thermodynamics like zeroth, first, second, as well as third law, here we are going to focus only about the first law of thermodynamics, followed by the second law of thermodynamics. I hope all of you know what is meant by the first as well as the second law of thermodynamics. So first law of thermodynamics simply talks about the conversion of energy from one form into the other form. It is not going to talk anything about the direction. It only talks about the energy is conserved, whether the heat into work or work into heat. That is what we are going to define about the first law of thermodynamics. First law of thermodynamics simply says that the energy is conserved. It is not going to mention any direction for a particular process. Coming to the second law of thermodynamics, because of the limitations of the first law of thermodynamics, we will be focusing about the second law. And in this second law of thermodynamics, based on the concept called as entropy, we are going to focus about the second law of thermodynamics. Here in this second law, we are going to talk about the direction, and also we are going to focus about the energy conversion. That is the reason second law of thermodynamics is also called as the qualitative. Second law of thermodynamics is called as the qualitative law, whereas the first law of thermodynamics is considered as the quantitative. First law of thermodynamics is considered as the quantitative law. So I'm not going into detail, just I want to introduce about the thermodynamics and the different laws which we are considering here. So whatever the amount of work or heat produced depends upon the thermodynamic thermodynamic values for reversible reactions. Here we also talk about the reversible process as well as the irreversible process, just like whatever we are going to learn in our basic thermodynamics part. So more specifically, here the main intention here is to combine the hydrogen and oxygen. So we are going to talk about the hydrogen as a fuel in the fuel cell, followed by oxygen, which we are going to consider it as an oxidant. Okay. And coming to the reaction here, we are going to talk about the heat work as well as the water as the product. So this is what we are going to focus in our thermodynamics of the fuel cell. That is what we are talking about. So more specifically, it becomes hydrogen and oxygen to produce electricity with water and heat as its byproduct. And the energies we are going to consider in the thermodynamics here are, one is the chemical energy. That chemical energy is getting converted into the electrical energy. So when a fuel cell is operating, some of the input is used to create the electrical energy, as we know, and the remaining portion is converted into the thermal energy depending upon the type of the fuel cell we are considering. So again here, one more concept is going to talk about, we need to focus about, which is nothing but the Kelvin-Planck statement. Kelvin-Planck statement. Because whatever the amount of energy which is being generated, that complete amount of energy cannot be converted into useful work, which means some amount of energy is getting converted into electrical energy and remaining amount of energy is being converted into thermal energy depending upon the type of the fuel which we are using. So that is what we are concluding here. So based on the first and second law of thermodynamics, one can analyze thermodynamic potential to specify how energy can be transferred from one form into the other form. So here we are talking about from the basic laws of thermodynamics, how the energy conversion is taking place and how the what is the working principle of the fuel cell. That is what we are going to discuss about. One second. So coming to the as I have mentioned already in my previous slide, that the hydrogen and oxygen are considered as the simplest case for our analysis, and that I have already written in my previous slide. So a general thermodynamic analysis of hydrogen fuel cells of the reversible work for the reversible reaction is performed. Okay. And the concepts of the enthalpy, specific heat, entropy, and Gibbs free energy are related to the reacting systems in the fuel cells. So whatever the enthalpy which we are talking about here is nothing but the total heat content of the system. And coming to the enthalpy, basically as such in thermodynamics, we don't have any definition for enthalpy. So in order to simply replace the internal energy plus flow work, we are considering it as enthalpy. That is how we are going to define. And it is a thermodynamic property, and also we can consider it as an extensive property. And then coming to the specific heat is nothing but we are going to talk with respect to Q is equal to MCP delta T or MCV delta T. Specific heat is nothing but what the amount of heat energy required to increase the temperature of a substance by 1 degree Celsius. And again, entropy is one more thermodynamic property which is very, very important. And this entropy is nothing but measurement of the molecular disorderness. Entropy is nothing but what? The measurement of the molecular disorderness. So when we say that molecular disorderness, basically entropy is not at all desirable. And then comes the Gibbs free energy, where we are going to talk about the thermodynamic relations. And here the Gibbs free energy, we are going to denote it with delta G. We are going to talk about this in detail. So the concepts of enthalpy, specific heat, entropy, and Gibbs free energy are related to the reacting systems in the fuel cells, whatever we are considering. And whatever the Gibbs free energy which we are considering is the thermodynamic potential that measures the reversible work by a thermodynamic system at a constant pressure and the temperature. So we can say that the Gibbs free energy is nothing but the function of the pressure as well as the temperature. And already I discussed about the enthalpy, entropy. I have defined them and what is meant by specific heat. And then ultimately, whatever may be the device which we are going to consider, we need to improve the performance of it. So the efficiency of a fuel cell is the useful energy output which we are focusing about. So whatever the amount of energy which we are considering, or the amount of energy which we are supplying, out of which how much amount of energy is being converted into useful work, is the thing which we will be focusing in our analysis. So coming to the discussion outcomes. So this discussion basically examines how electrical energy and thermal energy are transferred in the hydrogen fuel system. It also defines how reversible fuel cell voltages, which are maximum fuel cell performance, are affected by the departure from the standard state. And then we will be talking about the basic thermodynamic concepts allow one to predict the state of the fuel cell system, including its potential, temperature, pressure, volume, and the moles of the fuel cell. So let's see what will be the discussion of the outcomes here. So let's start with the construction of the fuel cell. So coming to the construction of the fuel cell, basically fuel cell are going to be coming in many varieties. However, they all work in the same general manner. Basically, they are made up of three adjacent segments. One is the anode, followed by the electrolyte, and then the cathode. So basically, two chemical reactions occur at the interface of three different segments. Like I can say as we are considering anode, electrolyte, and cathode. So basically, two chemical reactions will be observed at the interface of the three different segments. And the net result of the reactions is that fuel is consumed, water or carbon dioxide is created, and an electric current is created, which can be used to power the electrical devices normally referred to as what? The load. This concept is simple. In how these fuel cells are working here, we are considering three segments. One is the anode, electrolyte, and the cathode. So between these three, we are considering two interfaces. So two chemical reactions are going to occur. So the net result of the two reactions, whatever we are considering, is that the fuel is consumed, which means we are talking in terms of the chemical energy, so that the water or carbon dioxide is created, resulting of the electrical current, and whatever the electric current which we are talking about, which is useful for power, generate the power electrical devices, normally referred to as what? The load. So coming to working of the fuel cell, let's see how this working of the fuel cell is taking place. So at the anode, whatever we are considering here, at the anode, a catalyst oxidizes the fuel. Usually we are considering it as hydrogen, turning the fuel into a positively charged ion and a negatively charged electron. This is the basic keyword which we need to remember. So at the anode, a catalyst oxidizes the fuel, usually what? Hydrogen. That is what I have earlier told in my first slide, turning the fuel into what? A positively charged ion and a negatively charged electron. And whatever the electrolyte which we are talking about, the electrolyte is a substance which is specifically designed so that ions can pass through it, but the electrons cannot. So which means what? Only the ions are going to pass through the electrolyte, but not the electrons. So whatever the freed electrons which we are considering, they travel through a wire, creating what? They are going to travel through a wire, creating the electric current. So the ions travel through the electrolyte to what? Now whatever the ions which we are talking about, okay, they are going to travel to the cathode, but whatever the electrons which we are talking about, they are staying back in the electrolyte itself. They are passing through the electric wire in order to generate the electric current. So once reaching the cathode, whatever the ions which we are talking about, again they are reunited with the electrons, and the two react with what? A third chemical, which is nothing but usually oxygen, to create the water or carbon dioxide. This is how the fuel cells are going to work out. You can see the reactions which I have given here. So first, initially, we are talking with respect to the hydrogen as the fuel. So in this, what is happening? This, whatever the fuel which we are considering, it is turning out into a what? A positively charged ion and a negatively charged electrons. Okay. So ions are staying back in the electrolyte. So sorry, ions are traveling to the cathode, whereas electrons are passing through the electric wire and they are generating the electric current. Again, they are coming back and joining in the what? Cathode, so that here it is getting mixing with what? Oxygen. So this is how the fuel cells are going to work out. Now, let's see. What is the thermodynamics of the fuel cell? A fuel cell, also known as a galvanic or a voltaic cell, is a well-known example of a device that works by changing the chemical energy. Okay, by changing the chemical energy into electrical energy. I keep on repeating the same. Okay, which is exhibited in terms of cell potential and the electrical current output. The maximum possible electrical energy output and the corresponding electrical potential difference between the cathode and anode are achieved when the fuel cell is operated under what? The thermodynamic reversible conditions, which is very, very, very important. And also it is very important that some amount of energy, heat, we are unable to utilize it. This particular heat is being dissipated. So if you see here, the same thing I have explained in my previous slide, hydrogen and oxygen is entering the thermodynamic system, which is getting converted into the electrical work, which is the useful work, and remaining amount of energy is dissipated, and some amount of energy is getting converted into what? Some amount of energy is getting converted into water. So now whatever we have discussed there, this is what the reaction which I was talking about. The electrochemical reactions which is occurring inside the fuel system is nothing but the hydrogen mixing with oxygen, which we are calling it as an oxidant, and it is getting converted into electrical work, heat being dissipated, and water is the product. This is what I said, where W is nothing but the rate of electrical work done by the system, and Q is the rate of heat transferred into the system from the surroundings at constant pressure and temperature. And coming to the electrical work, basically it is described by the relation that W is equal to EI delta T, where E is nothing but the cell voltage and I is nothing but the current. So basically in a fuel cell reactions, electrons are transferred from the anode to the cathode, generating the current, which already we have discussed. So just I will give the basic expressions, and whatever the amount of electricity I delta T which transferred when the reaction occurs is given by NF, where N is nothing but the number of electrons transferred and F is nothing but the Faraday's constant, which is nothing but 96,493 coulombs. So whatever the electrical work can hence be calculated as W is equal to minus NF E cell. Okay. And coming to the Gibbs-free energy, which I told that, which is very, very important, is the maximum amount of work done by the system. I can say that the available energy in our thermodynamics concept. So electrical work is nothing but, we can write it in terms of delta G, where delta G, whatever is nothing but the Gibbs-free energy, can be written as minus NF E cell. And the maximum cell potential or the reversible cell potential becomes in terms of as minus delta G upon NF. I did not do anything new here. Just I have rearranged the terms and I have written the expression. So where E degree is nothing but here the reversible voltage is nothing but the reversible voltage, because it is the maximum possible voltage without any irreversible losses. And this is the maximum possible voltage of an electrochemical cell. Okay, since it is assuming a reversible process. So always, why we are talking about the reversible process? Reversible process is nothing but a practical process in which we can assume maximum efficiency, which means we can say 100% efficiency is possible. That is the reason always we talk in terms of the reversible. Coming to the irreversible process, in case of irreversible process, we assume that some losses are being considered, and those losses are nothing but they are getting dissipated in the form of heat. And obviously, the efficiency of the irreversible process will always be less than the efficiency of the reversible process. And one more important observation you can make here is, if all the potential chemical energy for a reaction went into the electrical work and there was no heat transfer, which means no heat dissipation, which means what? There would be no entropy change. So what is the entropy? Entropy is nothing but the measurement of molecular disorderness. And basically the entropy, we are going to write it in terms of ds is equal to dq upon t. If it is a reversible cycle, if I am going to consider it as an irreversible cycle, the change in entropy can be written as a dq upon t, the quantity dq upon t, plus the entropy generation, plus the entropy what? The entropy generation. So whenever we say that whatever the amount of energy, chemical energy, which is getting converted into the electrical work, and there is no heat transfer, which means your dq term is 0, which means the change in entropy is also what? 0. There is no entropy change. But whereas in the case of the irreversible process, even though there is no heat transfer, but still your change in entropy is not 0, it is a positive, because entropy generation is always a positive quantity. What is that, friends? Entropy generation is always a positive quantity, and it is not a property. It depends upon the extent of irreversibility. So if in the reversible case, whenever we talk about the reversible process, if the chemical energy is getting converted into the electrical work, provided there is no heat transfer, which means there is no entropy change, in such case, your change in the Gibbs energy is equal to the change in the enthalpy, which is nothing but we are going to talk in terms of the Helmholtz function. So in the earlier case, we have written that for the reversible case, it is written in terms of minus delta G upon NF. As I said that dg is equal to dh, this is what the expression we have written. So coming to the features of the fuel cell, basically the electrolyte substance, which usually defines the type of the fuel cell and can be made from a number of substances like potassium hydroxide, salt carbonates, and phosphoric acid. And the most common fuel used in the fuel cell is hydrogen, as I have already mentioned. And the anode catalyst, whatever we are talking about, usually it is a fine platinum powder, breaks down the fuel into electrons and ions. And the cathode catalyst is nothing but often nickel, which converts the ions into waste chemicals, with water being the most common type of waste. Here we are talking about the materials we are going to consider in anode as well as the cathode, and as well as we are talking about the electrolytes and all. And the gas diffusion layers that are designed to resist the oxidization. So these are the features of the fuel cell. And coming to the types of the fuel cell, basically fuel cells are classified based on the type of the fuel and the oxidant, as well as based on the type of the electrolyte. So coming to the based on the type of the fuel and oxidant, they are classified as hydrogen oxygen fuel cell, hydrogen oxygen fuel cell, hydrogen air fuel cell, ammonia air fuel cell, and hydrocarbon air fuel cell. But predominantly, most of the times, majority of the times, we will be using the hydrogen oxygen fuel cell. And based on the type of the electrolyte, basically we will be considering the phosphoric acid fuel cell, alkaline fuel cell or alkaline fuel cell, then followed by solid polymer fuel cell, molten carbonate fuel cell, and solid oxide fuel cell. This is where the area on which my PhD scholar is working on. So coming to the based on the types of the electrolytes, as I have mentioned, basically for alkaline fuel cell, the operating temperature will be between 150 to 200 degrees Celsius, and the unit size will be between 5 to 300 kilowatt. And basically the alkaline fuel cells we are going to apply in the space and militaries. And coming to the proton exchange membrane fuel cell, PEMFC, basically its operating temperature is between 5 to 100, and the unit size is between 50 to 250. And basically this PEMFC electrolytes we are going to use in the residential, portable laptops, cellular phones, video cameras, bus, cars, railway, and locomotives. Majority of the times we will be using this PEMFC electrolytes in our majority of the day-to-day needs. And coming to the phosphoric acid fuel cell, it operates between the temperature of 160 to 210 degrees Celsius, and the unit size is between 5 to 200, also for the megawatt size plants, and it is a dedicated power for railways. And moltenate carbonate fuel cell, and the operating temperature is somewhere between 600 to 650 degrees Celsius, I can say, and the unit size is between 100 to 2000 kilowatt, and basically it is a dispersed power and utility power we are going to use there. And coming to the solid oxide fuel cell, the operating temperature is between 800 to 1000, and we are going to the unit size of these type of electrolytes where we are going to use are 2.5 to 250, and domestic and commercial utility power, mobile application for railways are used. And direct methanol fuel cell, the operating temperature is between 50 to 120, and the unit size is between 0.1 to 1, and for portable electronic devices we will be using. So let's see what are the advantages and the disadvantages of the fuel cell. So coming to this, so these are the different electrolytes which I was talking about. So the advantages, coming to the advantages: quick startup, easily available auxiliaries, water management, but they are susceptible to impurities. And coming to AFC electrolytes, reliable but handles carbon dioxide poorly. And coming to the MCFC electrolytes, they can operate with a wide range of fuels. High temperature, corrosion, thermal fatigue are some of the disadvantages. And for SOFC, solid oxide fuel cell, can operate with wide range of fuels, but expensive auxiliary parts at the slow startups. And most of the focus we are going to for the international efforts are on PM as well as the SOFC. So these are the reactions in the different fuel cells. Like starting with the left side, I have given the electrolytes and anode, electrolyte, and cathode, and hydrogen. In most of the cases, we have considered hydrogen as the working fluid only, that is the fuel, and electrolyte, how the reactions are taking place, and this is what the cathode. And just for your understanding, I have included this slide, and followed by what the materials used in the different fuel cells. You can see in PEM, PAFC, what are the materials we are using in case of anode, electrolyte, as well as the cathode, and in case of AFC, MCFC, SOFC. This is just for your understanding purpose. Okay, so whenever we are trying to design or fabricate the fuel cells, so these are the points which we need to consider. And coming to the most important part, the voltage and its losses in the fuel cells. Basically, the open circuit voltage for a cell is typically assumed to the equilibrium Nernst potential for the overall electrochemical reaction. So Nernst equation is very, very important. It is more appropriate to calculate the average Nernst potential using partial pressures of chemical species at cell inlet and exit, because of the decreasing cell voltage from inlet to the exit of the cell. So basically, these are the equations we are going to consider. These are the equations we are going to consider for the Nernst equation. So at the inlet and the exit, and normally this is how we are going to define, where R is the universal gas constant, T is the cell temperature, P is the partial pressure for the respective species, I and E are nothing but the cell inlet and the exit respectively. And coming to the voltage loss, which I have already told you, as the cell begins to supply the current to an external load, it moves away from the state of equilibrium, and the operating voltage drops due to the irreversibilities associated with the internal charge transfer, conduction, and the diffusion process. Yes, it is true, because whenever we talk about the thermodynamic system, basically in thermodynamic system, we are going to measure the properties only when it has attained the thermodynamic equilibrium condition. So when the energy is being passed, so what is happening? It is moving away from the state of the equilibrium, And what is happening? The internal energy is going to drop. That internal energy we are going to talk in terms of the voltage. So why this is happening? Due to the irreversibilities associated with the internal chance transfer and the conduction as well as the diffusion process. So these irreversibilities are individually categorized as ohmic, activation, and concentration polarizations. And these polarizations can be considered as what? Voltage losses, and they are given as follows. So basically we are going to consider, okay, going to consider ohm loss, okay, ohmic, activation, and concentration polarization, and this is what we are going to do. So accordingly, the cell voltage can be expressed as what? Nernst voltage minus the loss. In this loss, we are going to consider all the three. So coming to the ohmic polarization, it is related with the electron and the ion transmission process, which is going to take place in the electrodes, electrolyte, and interconnects resistance across each material interface. The cell ohmic resistance is calculated with sum of each component respective resistance as a series electrical chemical scheme based on the Ohm's law. So basically, I don't want to go much into detail of these losses and all. Basically, these are the standard concepts. So the definitions, like what is ohmic concentration, what is the activation, and the other parts. So these are the ohmic polarization curve which has been taken, okay, for the different electrical, okay, and then followed by the activation polarization, one of the losses which we will be considering. And basically here the chemical reactions, including the electrochemical reactions, which are involving the energy barriers that must be overcoming by the reacting species. And for activation polarization, basically we'll be considering the Butler-Volmer equation, which is used to compute this activation polarization. So this is one losses, okay, and the corresponding equations which we are going to consider for calculating, and this is what the graph which we will be getting. And then the concentration polarization, the third voltage losses which I was talking about. And this concentration polarization involves the difference in partial pressure between the electrode electrolyte interface and the bulk of the gas streams. So the electrochemical reaction at anode section results in the hydrogen consumption at the electrode electrolyte interface, and the partial pressure of the hydrogen decreases when it is not readily replaced from the fuel cell. So these are the different losses which I was talking about, and the concentration polarization, and these are the expressions which we will be considering, and this is how we are going to calculate them, and these are the some of the expressions, okay, which we will be using for calculating. And this is what the corresponding graphs which we have taken, which is available in the open literature. And the most important thing which I want to focus here is about the low temperature fuel cell as well as the high temperature fuel cell. So basically this is the hydrogen oxygen, basically air fuel cell, which I am considering. So similarly, whatever we have discussed initially, so we'll be talking about anode, electrolyte, cathode. So hydrogen is entering the thermodynamic system, and air is entering here, and nitrogen as well as water is leaving, and these are the reaction mechanisms which we are talking about, and how the electrical work is being produced, and what are the products and all. So coming to the, as indicated in the figure, as I have told you, the protons are going to leave the hydrogen electrode and enter the electrolyte, leaving behind the electrons that give the hydrogen electrode a negative charge and polarity. Already we have discussed about that, okay. And coming to the, just I have explained you, I don't want to read out all this. And coming to the low temperature fuel cell, basically we'll be talking about the direct methanol fuel cell, or DMFCs, are a subcategory of proton exchange fuel cells in which methanol is used as the fuel. Their main advantage is the ease of transport of the methanol, and energy dense at reasonably stable liquid at all environmental conditions. And basically these are the equations which we are going to consider in case of anode, cathode, and the overall reactions, okay. And the applications of the DMFC are limited in, basically current DMFCs are limited in the power they can produce, but can still store a high energy content in a small space. They can produce a small amount of power over a long period of time, which is very, very advantageous. This makes them ill-suited for powering large vehicles, but ideal for smaller vehicles such as forklifts and tuggers, and consumer goods such as mobile phones, digital cameras, or laptops. And even it is helpful for the military applications of DMFCs are an emerging application since they have low noise and thermal signatures and no toxic effluent. There are many advantages of this DMFC. Okay. And coming to the high temperature fuel cell, though, basically we'll be talking about the molten carbonate fuel cell. Molten carbonate fuel cell. So again, for this same hydrogen, oxygen is entering, and this is what the anode, electrolyte, cathode, the same fuel cell which we discussed about. So water and heat out, and carbon dioxide is in here in case of molten carbonate fuel cell, and this is what the chemical reactions, okay, which is taking place. So basically here, in case of molten carbonate fuel cells, basically they are considered as the high temperature fuel cells that operate at temperatures of 600 degrees Celsius and above. And basically molten carbonate fuel cells are recently developed type of fuel cells that target small and large energy distribution generation system, since their power production is in the range of 0.3 to 3 megawatt range. And during the production of carbon dioxide, during reforming of the fuel cell, MCFCs are not a completely green technology. That is one disadvantage, but are promising due to their reliability and efficiency, that is sufficient heat for cogeneration with electricity. So this is one of the advantage of using this molten carbonate fuel cell. But improved efficiency is one very good reason in case of MCFCs, which offer significant cost reduction over phosphoric acid fuel cells, PAFCs. And most of the carbonate fuel cells can reach efficiencies approximately up to 60%, considerably higher than 37 to 42% efficiency of the phosphoric acid fuel cell plant. So these are the some of the applications and like how high temperature fuel cells are going to work, their applications, advantages, as well as the low temperature fuel cells. And this is what the application which I was talking about. So molten carbonate fuel cells were developed for natural gas, biogas, and coal-based power plants for electrical utility, industrial, and the military applications. And this is what the solid oxide fuel cell on which my PhD scholar is working now. So basically, again, the same fuel inlet, hydrogen, air inlet, oxygen, that is oxidant, and whatever the electric current. So how the ions and the electrons are getting separated and which is moving, and already I have explained. And unused gases are going to move outside, and the excess fuel and water is also coming outside. So solid oxide fuel cells are a class of fuel cells characterized by the use of a solid oxide material as the electrolyte. And basically, SOFCs are used to conduct negative oxygen ions from the cathode to the anode, and they are going to operate at a very high temperature, typically between 600 to 1000 degrees Celsius, which I have already explained during the electrolytes discussion. And basically at these temperatures, solid oxide fuel cells do not require expensive platinum group metals catalyst as it is currently necessary for lower temperature fuel cells such as PEMFCs, but are not vulnerable to carbon monoxide catalytic poisoning. However, you need to remember here that vulnerability to sulfur poisoning has been widely observed, and the sulfur must be removed before entering the cell. So these are some of the precautions which we need to take, okay, before doing some analysis in this particular part. So this is what the reactions in the solid oxide fuel cells which we will be observing. So this is the reforming reaction, the shift reaction, what is happening in the anode, cathode, and this is what the overall reaction which we are going to observe. And this is what electrical work, which is 4 times of the Gibbs free energy. So already I have explained about the solid oxide fuel cells and how they are going to work out. And coming to the applications of the solid oxide fuel cells, basically they are having the wide variety of applications from use as auxiliary power units in vehicles to stationary power generation with output from 100 watts to 2 megawatts. And how we are going to calculate the fuel cell thermodynamic efficiency, which is very, very important. Basically, it is defined as the actual electrical work to the maximum available work, which is nothing but I can say in terms of available energy, we can define them. So actual electrical work we are getting here is in terms of the Gibbs free energy, and the maximum available work is nothing but delta H. So that is what we have expressed here. And the maximum possible thermodynamic efficiency of a fuel cell can be written as T delta S upon 1 minus T delta S upon delta H. So basically, assuming that we are completely considering that it is a reversible case and the Gibbs free energy can be converted into electrical energy, then the maximum efficiency which we can expect is 83%. Whereas for the hydrogen, for the LHV, like low heat cases, the fuel efficiency would be somewhere around 94.5%. So this is how the efficiencies we can expect by considering certain changes. So coming to the conclusion, basically the thermodynamics is used to understand the process of energy conversion in the fuel cells. The determination of a fuel cell's performance depends upon the thermodynamic evaluation. Whatever the heat potential of a fuel is given by the enthalpy of the reaction, and not all heat potential of a fuel can be used to perform useful work. That already we know, because heat is considered as the disorganized form of energy. And the reversible work of a fuel is defined by the Gibbs free energy, which I have already told you, which is nothing but the electrical work. And the study of the electrical effects show that the molar flow of the fuel used is proportional to the electric current, and the reversible work is proportional to the reversible voltage. And whatever the irreversible losses which causes a difference in the efficiency of reversible and real process, with efficiency of the always less than the reversible, that we know, because always efficiency of the irreversible will be less than the efficiency of the reversible. The losses are due to two major reasons. One is the irreversible kinetic losses and the fuel utilization losses. So these are the conclusions which we can make from the basic thermodynamics of the fuel cell. So if you're having any doubt, okay, you can ask.
Thank you, Dr. Santosh.
Thank you, sir.
Now, I think there are some questions in the chat box. We'll just give the chance to them. Just one second.
Yes, we can use lithium-ion battery also as a small fuel cell for our analysis. Yes, we can do that, Shankar.
Shankar sir, if you have further doubts, I am unmuting you. You can ask the speaker.
Thank you, sir. Thank you very much.
Thank you. Anybody else from the participants? Lakshmi Kumari from MGCET. What is the cost of fuel cell technology, sir?
See, basically, here we are, as of now, even we are doing the simulation only. And especially we are focusing on the Bresson cycles in order to work by using the solid oxide fuel cell. So we did not plan anything related to the like fabrication of this fuel cell and all. So even I too don't have the particular idea like what would be the cost of it. So
Money one,
yeah, he has written, yes, I will definitely share the PPT with the coordinators. You can please collect it from. So basically, coming to the software, we can use with we can go with the MATLAB coding, and also even we can do with the normal simulation also by using ANSYS Fluent and all. We can go for with that basically, but we are using MATLAB by doing the coding, and we are doing the analysis.
Muthukumar sir, is it okay or you want to ask further? I have unmuted you.
Thank you.
Hello.
Pooja.
Sir, good morning, sir.
Good morning.
Yes, sir. Hello. Sir, actually, are using MATLAB for coding purpose. Can we get the performance of the fuel cell using this MATLAB, sir?
See, like normally what we are doing in order to evaluate the performance is using the analytical part only. We are using the equations for simplifying them.
Okay, sir.
Okay, yes, we can even for calculating the performance and all, we'll be going with the analytical part. In the simulation part, basically we can observe how these like reactions are taking place, and only as it is going to play a minute part in that.
Okay. Can we get the current density and voltage output from the MATLAB, sir, using MATLAB?
Yes, definitely. We can do it.
Okay. So which is best one, sir? Is it for ANSYS or MATLAB? Which one is best, sir, for this?
See, we are using MATLAB.
Okay, sir.
That is what I can share with you.
Okay, sir. Okay, sir.
So if you want, you can see some of our publications on this particular part which we are doing, and one paper has been communicated also. I will try to share that particular paper for your understanding also. I will share it with the coordinators. They may share it with you.
Thank you, sir. Thank you, sir.
Anyone else would want to?
Yes, Amar Kumar. Solar technology is more useful for FCT. Because we are talking about the waste heat, right? So when we talk about the waste heat, so that can be converted into some other form of energy.
One more message.
So coming to the advancements, as I said that we are working basically in case of turbo machinery part, especially in terms of, as I said, we are focusing on the Bresson cycle, Breton plus Ericsson cycle. That is what we are focusing about by using the solid oxide fuel cell. So these are the advancements in the sense, especially we can focus on the electrical vehicles, vehicle technology and all that can be done. And even the battery thermal management system also, the fuel cells may be applied. There is a good scope for the advancements.
Gopi Krishna, I have unmuted you. You can ask the question, please.
So what will be the future market share of SOFC and PEMFC, which is going to dominate more among two? See, we are not focusing on any economical analysis and any other part. As I said, even in my initial presentation itself, even we are also new to this particular area. We are in the learning process, and the cost analysis, economy analysis and all, maybe in the later part of our research work, we will be focusing upon. So as of now, as I told you, especially we are working or mainly focusing on the development of this Bresson cycle, and by utilizing the solid oxide fuel cell, that is what we are doing. Yes, I do agree with you. Presently, PEMFC is well established and mature technology and easy to use. I do agree with you. But coming to the future market, I can say that maybe solid oxide fuel cell may get some better edge than the PEMFC. It is my expectation.
Thank you so much, sir. Santosh sir, thank you very much for your.
Thank you, sir. Thanks a lot. Thanks a lot. Actually, I'm having one more session from 12:15. That's the reason I have to little bit.
Okay, sure, sir. Thank you your kind presentation, and also the knowledge whatever you share from us. Actually, sir started from the scratch, actually from thermodynamics to fuel cell. So it is a long journey.
Sir. Even as I said, I am also in the learning stage of this fuel cell and all.
Yes,
okay.
Yes,
so first of all, once again, I would like to thank Dr. Jivtesh Kumar Panda sir and Vishwanath sir for giving me an opportunity for delivering this guest lecture. And thank you. Thanks a lot.
Thank you, sir. Bye.
Thank you. Bye, sir.
Bye. Now, I would like to welcome our next speaker for the second session. In fact, I am very delighted to invite him for this, and he is kind enough to accept to deliver a lecture. I request all the participants to actively participate in his talk because he is very much qualified and very experienced. I just wanted to introduce him with a brief introduction about him. So, Dr. Gaurav Gupta is at present a lecturer in chemical engineering at Lancaster University. His research interests involve electrochemical engineering, catalyst development for energy storage and generation systems, electrolysis, fuel cells, nanomaterials, renewable energy, and corrosion. After graduating with a degree in metallurgical and materials engineering from National Institute of Technology, Rourkela, India in 2007, he went on to do a master's in materials and metallurgical engineering from IIT Kanpur, India, where he developed his interests in electrochemistry and materials development. He was offered a College of Engineering and Physical Sciences scholarship to do his PhD from 2010 to 14 on development of bimetallic platinum chromium electrocatalysts for proton exchange membrane fuel cells from the University of Birmingham, working with Professor Paula Mendes and Dr. Surbhi Sharma, who is our first speaker. He joined as a postdoctoral researcher in 2015 on an Innovate UK project at Imperial College London on the development of low-cost proton exchange membrane fuel cells in partnership with Warwick Manufacturing Group, WMG, Arcola Energy, Lohmann Technologies, Fourth Energy Wave. In 2016, he joined Newcastle University as a research associate, where he worked on various projects related to alkaline fuel cells, alkaline electrolyzers, and catalysis. Today, he is going to deliver his talk on alkaline fuel cells and electrolyzers. So we are very much grateful to you, sir. And the session is now been handed over to Dr. Gaurav Gupta. Thank you very much, sir.
Thank you, Dr. Vishwanath, for the introduction. I was not really expecting that much details in there, but thank you so much for your kind words.
Thank you.
So I'm just going to share my screen so that I can share the. Okay. I hope everyone can see the screen, right?
Yes, we are able to see. Yes.
Okay. Okay. So I have kept it slightly different, and I think the previous session sits very well with my talk. So it will be easier for me to explain certain things, as doctor has already explained. I think it was Dr. Santosh, right, who was giving the last lecture.
Yes.
So yeah, so it will be easier to understand as well. So I think Dr. Vishwanath has already explained my career journey. I started from NIT Rourkela, and now I'm sitting in Lancaster University after doing a couple of degrees and then doing some postdocs at Imperial and Newcastle University. So I will not go into much details than that now. So where are we now located? So we are located here in the northwest region of UK, so very close to Blackpool and Manchester. So Manchester is one of the major airport closer to us. And this is our campus and the building where I normally work in and inside of building. So just wanted to give an insight of what the situation is like here. And we are very close to nature. So you can come here and see the nature. You can go out. So it's very nice during the summers. It gets a bit cold during the winters, but it's a nice place to stay and live as well. Okay, now moving on to the talk. So first thing I will focus on is electrolyzer, and then the second part of the talk will focus on fuel cell technology. So I will be covering why we are working on electrolyzers, what are the different materials we use for electrolyzer, how we test them, because we normally test them ex situ just to make sure that we are making something good, and then only we go on to test it in real fuel cell system or electrolyzer system, and then I will give a conclusion on what we have done so far. So this is I will be sharing my research as well as the research where my colleagues did when I was working at Newcastle. So why we are working on electrolyzer? Currently, only 5% of more than 500 billion meter cube of hydrogen which is generated comes from electrolysis. Most of it comes from steam reforming, which pollutes the environment because there is a lot of CO2 generation. That's why we are moving towards electrolysis, so that we can try to generate more hydrogen using this way and get rid of CO2. As I think in the last lecture, there was a question, PM technology is very mature and advanced. So why we are not focusing completely on that? Why we want some alternative? PM is very good, but they are very expensive because we use precious metals in them, and that catalyst only costing like 50 to 60% of the wholesale cost. So that's why we want to move towards something which uses non-precious materials so that you can bring the cost down. Liquid alkaline system, it is very well established, but the problem comes that you cannot really compress the hydrogen which you are producing because there is very little chemical separation between the gases. So that's why you want something which can combine the PEM technology and the AEM technology, and that's where alkaline AEM comes in. Because you will have better separation, you can operate at different pressure, and it is easier to compact and very flexible. And if you are using AEMs, you will estimate the cost estimation is like 43% reduction. And this is done by analysis is done by ITM Power, which is one of the established company in UK. And some of the cost analysis, like 50% of the cost of kilogram of hydrogen produced through electrolysis is the electricity which is used in there. So the major cost in electrolysis is the electricity. So that's where you want to look at renewable resources like solar technology, as discussed in last lecture as well. Like solar technology will go very well with the fuel cell technology, electrolyzer technology. But the problem in UK, we get very little sun. So solar technology is not going to be that great in UK, but it will be great in India or Middle Eastern countries or Africa, where you get a lot of sun. So what is the basic difference between AEM and PEM? So this is just a general picture of AEM technology on the left side and PEM technology on the right side. The main difference is the membrane which is used inside. So the membrane separation, one can only let protons through, the other can let hydroxide ions through, and that causes the change in the reaction. So the reaction on the AEM side is you have 4 water molecules and 4 electrons forming hydroxyl ions. The hydroxyl ions transfer to the membrane to the anode side, and that's where you generate water and oxygen. So hydrogen is generated on the cathode side, whereas oxygen is generated on the anode side. So it's the ion which defines whether it is an alkaline or PEM or acidic, because it is as a hydroxyl group. Okay, and on the PEM side, you have 4 protons reacting with 4 electrons, giving you hydrogen on the cathode, and on the anode, you have water reducing to 4 protons plus oxygen and releasing 4 electrons. So these are the protons which transfer from anode to cathode, and thus the reaction for hydrogen formation. So this is the basic difference between AEM, PEM. But the overall reaction stays the same, which is water getting reduced, forming hydrogen and half a molecule of oxygen. Yeah. So what are the challenges in AEM technology? It is the mobility of the hydroxide ion. It is very slow compared to proton ion because of the size of the hydroxide ion. The mobility reduces. It's like 1 to 1.6 times or even slower than that of the proton. And you require 2 moles of water per 1 mole of hydrogen in case of AEM compared to 1 mole in case of PEM, as you can see from this reaction. So you are using 2 moles of water for every mole of hydrogen, whereas you are only using 1 mole of water for every mole of hydrogen. So that's the challenge. That's where you need to develop the membranes which are better at transferring the hydroxide ion because of their reduced mobility. And what the problem comes with membrane, as you try to increase their conductivity or water uptake or ion exchange capacity, you are reducing their mechanical properties. So you have to come at a balance of the mechanical properties with their other properties like conductivity and IEC. So you have to reach the optimum there. Now, what is the difference between a fuel cell and electrolyzer? Basically, they are opposite to each other. So in fuel cell, you are using hydrogen and oxygen and forming water and energy, whereas in electrolyzer, you have water and energy and you are producing oxygen and hydrogen. So they are reversed to each other. So lot of the membranes and catalyst material can be used in both the things. But depending on the reaction, you might have to use oxides at some places and metals at other places. So we will discuss a little bit of those in later. The difference, I already told what is the difference between the electrolyzer technology, PEM and AEM. So this is the difference between a simple alkaline electrolysis system and a PEM electrolysis system. So you have the membrane for PEM, whereas you have a diaphragm in a normal alkaline system. So what we are trying to do is combine these two technologies, take the catalysis part from here, and instead of the diaphragm, put a membrane in there so that it is a compact system and you can compress and work it properly. So the reactions you are taking from alkaline system, but you are taking the setup from PEM system and combining them to make alkaline AEM systems. Okay. Now, let's talk about some of the materials you will be using for the alkaline electrolyzers. So, okay, I think this has messed up the slide. So I'm not going to go in detail about the methods we use to make catalyst. There are plenty of methods. You can use hydrothermal method, you can use arc melting, you can use chemical synthesis. There are different varieties of method. It depends on what structure you are looking at. Like you see, you can make nanowires using hydrothermal method, or you can make nanopowders using arc melting. The particle size matters because you are making oxide of manganese oxide. So the diameter or particle size is like 20 to 50 nanometers. So you are not making like 2 to 5 nanometer particles, which you make in platinum cases for fuel cell. For electrolyzer, the particle size is slightly more, but you are more worried about the surface area because that's where the reaction is going to happen. So the better surface area, you will have more activity because you are having more sites for the reaction to happen. And you can characterize them using X-ray diffraction. So that will define what the structure is like, whether it is a BCC structure, FCC structure, BCT structure, and whether you have impurities in that or whether it is a completely pure structure. Like in this case, it is a 25% beta manganese oxide and 75% Mn2O3. So you are having a mix of Mn2O3 and MnO2. That can affect the properties because MnO2 is a very good catalyst, whereas beta MnO2 is not. So you have to define what exactly you are trying to make and modify your method accordingly. So this is just one example regarding that. So one part is catalyst. You need membrane, as I was saying. You are replacing the diaphragm with membrane. So this is one of the membrane which was developed by our group at Newcastle. So we are taking basic polyethylene because that's the cheapest material in terms of polymers. You combine that with vinyl benzyl chloride, you expose that to gamma radiations, and you are having a functionated group of polyethylene with vinyl benzyl chloride. So you have this chlorine group here, and when you expose it to the TMA, which is tetramethylamine, you replace that group with amine group. And now this membrane is functionalized and it can be used for the transfer of the hydroxide ions, which is required for your anion system. So what you are measuring here in terms of the membrane characterization is degree of grafting. How much vinyl benzyl chloride is actually getting attached to the system. So that can be measured using this simple formula. Weight of the polymer before irradiation, weight of the polymer is this. After irradiation versus weight before irradiation. So this simple formula can give you what is the degree of grafting. Degree of grafting is important because if you graft it too much, it's going to become very fluffy or soft. If you graft it too little, you will have very thick membrane, which is not going to conduct. So you have to decide how much crafting you need, so that you will have both properties. You will have the mechanical strength as well as the conductivity and other ion exchange capacity of the system. The simplest characterization technique is NMR. So you use NMR and see whether you have actually made the structure you are looking for. So this is just the labeling. So this is available as a paper online as well. So you can read more details on what actually you are measuring or how you are comparing the different points in this membrane. So this is a proton NMR. So you are looking at the hydrogen functional groups in there. Okay. You have made the membrane, but does it really work? Is it stable enough? So you do the stability testing. You can test it under nitrogen or oxygen. It depends on what atmosphere you are going to expose it to. So we will test it under normal nitrogen as well as oxygen atmosphere for a couple of months. So under oxygen, it's going to degrade much faster, but that is the environment you will be having inside the electrolyzer or fuel cell system. So that's why this is important. So you test that stability. It is just putting the membrane in a nitrogen atmosphere in a solution and leave it and measure the conductivity, or after some time, after every month or after every week, and see how it performs. So that's the simple test. Okay. So you need ionomer as well for the components of the fuel cell system as well as electrolyzer. So this is the ionomer which we synthesized at Newcastle. So what you are having is a copolymer group, styrene, ethylene, butylene group. So you are chloromethylating it and using tin chloride and CHCl3, which is your chloroform, and you are forming a chloride ion or chloride functional group at the chains. Again, same thing which we did with the membrane. You use DMA and replace this chlorine group with the ammonium group so that you can convert that into hydroxyl group later on, which is easier for conducting the hydroxide. Yeah, again, you can do the analysis using NMR, find whether you have made whatever you are trying to make, or you have made something else. So to make sure that we have done the chloromethylation, this functional group shows that the polymer is chloromethylated, which is referring to this part. And then when you replace that with TMA, this disappears. That shows that the ion replacement has been done properly. Okay. You can also characterize these ionomers or membranes using ion exchange capacity. So it is just the capacity to know whether they can conduct the ions properly and how much they can conduct. So we studied with respect to the reaction time, whether we are doing reaction for 5 hours, 2 hours, or up to 20, 30 hours, to see whether it does make sense to do it for longer time or shorter time is more than enough. And you see, the longer time reaction time you give, the better the ion exchange capacity. So you are getting around 1.91 millimolar per gram at 22 hours. So that's what we decided. After that, it is too long of a time for the characterization. So that's why we stopped at 22 hours. You can also check the conductivity of the material. So what you are doing is you are taking carbon paper as anode and cathode, putting the membrane in between and just measuring the resistance, impedance. And that gives you the conductivity. You are not having any catalyst in there. So this is the simplest method to measure conductivity in situ, because you are doing within the fuel cell or electrolyzer setup. Now, half cell testing. So half cell testing is normally done for catalyst to check whether catalyst is good enough or not. So you might see in literature papers that they only report results. So I just wanted to give you an idea how actually you prepare the sample for half cell testing. So you have your catalyst material, you make that into a catalyst ink. How you make that? So you dissolve it in a solution of water or ethanol or propanol, depending on the solubility of the catalyst you are using, whether it is a platinum-based catalyst or any other oxide-based catalyst. So you make a catalyst ink. depending on what proportion you want. You have a simple gold electrode. This is OER testing. That's why we are using gold, because gold is not active for OER catalysis. That's why we use gold in here. Carbon, the problem with carbon is it oxidizes or corrodes during the OER potentials. That's why we are using gold. So you drop some amount of catalyst ink on the gold, you let it dry. You can dry it in a normal atmosphere. You can use IR lamp, you can use a fan, anything is fine. As long as you dry it gradually, you don't want to over dry it quickly, because then you will form some patches on the surface, which will not give you a good performance, or which will not give you the actual behavior of the catalyst. After you have dried it, you just assemble the cell. So this is a 3-electrode cell. So you have your catalyst, which you have prepared as working electrode. Then you have your counter electrode as platinum mesh. We use mesh because mesh has much higher surface area, so it gives you more flexibility on the testing. Reference electrode, we are using mercury oxide because it is more stable in alkaline environment. AgA-JCl is stable, but only up to some limit. So that's why we prefer mercury oxide, or you can use electrodes which are not dissolved or which doesn't get corroded. Any other electrode is fine as well. Okay. And some of the different RD electrodes which you can use. So you see there are carbon-based electrode, gold-based electrode, platinum-based electrode. They are simple RD electrodes or ring disc electrodes where you can study the ORR, peroxide formation and all as well. Now, giving some results about noble metals first, because that's what everyone studies before they move on to non-noble, so that you can share or compare the performances. Some of the noble metals which we tested for HER included platinum, iridium. So you see, as we increase the KOH concentration, the performance improves, the onset potential goes back, which shows that the catalyst is performing slightly better. So I'm not going into detail about what is the performance at this point or that. It is just giving you an idea how the performance varies with respect to the solution concentration. And look at that. When you are alloying platinum with iridium, the performance improves as well. So that's where alloying comes into play. You normally alloy it because alloying gives to stability as well as improvement in performance. And on the other hand, you are using less amount of platinum, which is expensive. Now, looking at the stability, because performance is not always what you need the material to be stable as well. So you look at the stability of the material also. So some of the testing in stability, so you can see they are stable for up to 2 hours. So this was just a short stability test done in half cell test setup, just to see whether they are stable or not. So you just hold it at a certain potential and leave it for a couple of hours to see whether they are stable or not. And you can see they are pretty much stable at all these potentials. Again, you have two different types of reaction, HER and OER. So similarly, OER testing. So you see, we have materials and we have some oxides on them as well. So because oxides provide a little bit more stability when you are dealing with OER reaction, because that's oxygen evolution reaction. So platinum, it's not great, but when you have it on different types of oxide, the performance improves significantly. You see platinum with iridium oxide, the performance shoots up plenty of time. So that is at 0.1 molar. And if you look at 1 molar, it will be even more because you have better conductivity in a higher concentration solution, which is 1 molar KOH solution. But you are normally looking at going towards a lower concentration solution because then you have less corrosion effect or less degradation, because lower the concentration, lower the degradation. If you are working at higher concentration, it is not safe to handle and it is not stable. Okay. Again, we check the stability of these different materials at 1 molar KOH, and they are very stable for like couple of hours. Okay. Now, I showed you results of the noble metals, but that's not what we really want, or that's not why we are moving towards alkaline system, because the main advantage of alkaline system is you can use non-noble materials for these systems. That's where our focus lies, to develop non-noble materials, whether it is nickel-based material, copper-based, copper. So we are trying to use transition metal systems and making catalysts using them. So as I mentioned, for HER, you can use pure metals like nickel, cobalt oxide. So you see, you have nickel, higher performance, cobalt, very low performance. But when you alloy them together, your performance shoots up because you are making a different system and it is very active. So that's where alloying is necessary. That's why we alloy materials. Okay. And if you look at the stability, you can see the stability, it's improving. But when you are alloying, you have chances of leaching. So that's where you see nickel cobalt oxide, there is leaching of the material, even though you are seeing improvement in the performance, that is due to leaching, because you are having a side reaction present in the system, which is giving you the false current, which might be affecting the performance. So don't assume that if you have improvement in the current, it is always your catalysis which is doing the improvement. There can be other side reaction which are hindering or which are doing corrosion of the system, and you are getting a false positive. Okay. Now, looking at the activity of OER. So as I mentioned, you are using normal metal catalyst for AER, but you are using oxides for OER because oxides are more stable in the OER environment. So some example at 1 molar KOH for OER. So you have nickel cobalt big system, manganese cobalt, copper cobalt, or you have simple cobalt oxide. So all of these are performing better, but you see nickel based systems, they are much better compared to other systems. And this is just a simple test we are doing. Okay. And we had this cobalt oxide here. Now, if you try to alloy it with copper, like you use various concentration of copper and make the system, you will see an improvement in the performance. That's why you have multi-component system, oxide system, because it helps you improve the performance of the system by alloying. Okay, so this was all about half cell testing. Now, how do you really test it in an actual system, whether it's an electrolyzer system or fuel cell system? I'm again going to show you how you make the whole system prepare the system for testing rather than just going directly to the results. So you have your catalyst is again just like you had it for the half cell testing. You can use either hand painting or you can use spraying to spray this catalyst on the GDL, which is the electrode surface. It can be a carbon surface or it can be a titanium surface, stainless steel, depending on the system you are spraying it for. After you have sprayed, you have this catalyst layer on top of that material. So you prepare the same for other system. And then because you have little bit of ionomer in there, you need to activate the system. You have to change the chloride ion, which was present in the ionomer, to the hydroxide ion, because that will provide you the conductivity that will help you conduct the hydroxide ion through the system. So you soak them in KOH solution and you change the solution every 20 minutes. It is done for 1 hour just to make sure that all of the chloride is converted to hydroxide. You wash to get rid of the excess hydroxide present in the system. And then you assemble the cell. So this is a simple cell. You have the cell, you put your cathode first, then you put a gasket. It is to separate cathode from the anode so that there is no transfer of gas release from one system to another. You don't want to mix hydrogen and oxygen. Then you place your membrane on top of that, and you place your anode other way around, facing the membrane. So everything should be facing towards the membrane. And then you close the cell you tighten it. Depending on what system you are using, you might tighten it a little bit, or you might tighten it differently. So tightening and studying the effect of tightening is very important as well, because if you make it too tight, you might break the membrane or you might puncture the membrane. But if you leave it, you will have gas leakage. You will not have a proper contact of the system. So that's where tightening is also necessary. And then you have a simple electrolyzer setup. So this is the cell we assembled. We have two bottles. So it's a simple homemade setup. You have two bottles which have the KOH solution or DI water or whatever the solution you want to use for the system. You connect with potentiostat, the working electrode, because it's a 2-electrode system. So you have the working with the sense and counter with the reference. So you are just using a 2-electrode system, not 3-electrode system in this case. You have the heaters installed within the cell so that you can study different temperature setups with it. So as I mentioned, there are different catalysts you can study. So cathode, we are keeping it constant as platinum catalyst because you don't want to change everything in one go to study the performance. So we want to study the performance of the anode catalyst while keeping other systems same. So that will give you a better analysis of the results. Before you start going to the results, there are losses in the system. I think it was mentioned by Dr. Santosh in previous thermodynamics lecture. There are different losses in fuel cell and electrolysis. The losses being, you have membrane, it will have ohmic resistance. So that will create losses. It will be dependent directly to the current. At lower current, you will have very less losses. But as you increase the current, it goes linearly towards the losses. So you are having lot of losses just because you have a membrane which has higher resistance. So that's where you want the membrane which is very conductive and have very low resistance. And you have activation losses. So normally thermodynamically, our reactions should start at 1.23 volt, right? But it never starts at 1.23 volt. It always starts at 1.4 or 1.5 volt. Why? Because you have anode and cathode activation losses. So that's where the losses are there. So you can try to reduce those losses by developing new catalyst material which are more active. So that is dependent on the structure of material of the catalyst. Okay, so now going towards some of the performance results. So this is just a system, simple system. Iridium oxide as OER and platinum carbon as SGR. As I mentioned, we are just changing the OER electrode. So you see, even a simple change in solution, like going from DI water to 0.1 molar, your performance shifts significantly because you are providing conductivity within the solution, and that is affecting the performance. So you might have heard about Nernst equation, right? So it is directly dependent on the pH. So with every change in pH, you have a 60 millivolt shift of the system. So this is the same thing which you are observing here, shift in the system. Again, some platinum titanium OER with nickel stainless steel. So it is just giving you different subjects, different catalyst materials which we have tested, how stable they are. They are very stable for like 100 hours, 120 hours. They don't degrade too much. You will always see a sudden drop initially because you are suddenly exposing it from its open circuit or 0 volt or whatever the starting potential is to that change in the voltage directly. It is 2 volt. So that's why this straight spike comes. So if you take it gradually, you can get rid of this spike. So this is not really a significant thing. This is just an observation. Okay. Now, you have different catalysts. You can have different loadings of the catalyst. You see here, we have studied what is the effect of nickel cobalt oxide loading on the performance. So you had a 2 milligram loading, you had 10 milligram, 20, 30 milligram. So you can only go up to a certain loading, and after that, the performance starts going down. Why? Because even your catalyst has some resistance, right? So if you keep on increasing the resistance of the catalyst layer, you are going to start losing performance because you have to overcome that resistance. So that's why you can only increase the loading up to a certain extent. Suppose if we have a very good catalyst, nickel cobalt oxide, like this, you can compare the performance of this to platinum. But since platinum is very expensive, you can add more of nickel cobalt oxide, try to reach that same performance, but you can only go up to a certain extent. Like here, we can go only up to 10 milligram, because if we go higher than that, you start losing the performance. So that is due to the resistance of the catalyst layer. And that's where we will be studying some catalyst layer thickness that I think I have added it in fuel cell setup, not here. Okay. Like I mentioned, the concentration of the solution which you are using has effect on the performance as well. Like you are going from 0.01 to 0.1 to 1 molar. So you have a different performance issue. And as you go higher concentration, you have better performance because of the Nernst equation, simple thing. And you can see the resistivity improves because you are having a better conductive solution. Yeah, so this is all done at 20 degrees Celsius, but normally you would not want to operate at 20 degrees. You want to operate at higher temperature, and that's why we study the effect of temperature as well. So how temperatures helps you improve the performance. You see, resistivity improves, goes from 180 to 120 when you increase the temperature from 20 to 60 degrees Celsius. So that's one of the reasons the performance improves. Because you have less resistance at higher temperature, you are improving the kinetics of the reaction. Okay, and you can compare different catalyst materials. So we had different varieties of manganese oxide. I showed you nano rods or nano powders. You can have composite materials of manganese oxide. That's what we are currently working on. So I'm just showing you some initial results of these materials. Like even they can help you improve the performance compared to nickel cobalt oxide, which is considered one of the best catalysts currently in alkaline system. So by combining manganese oxide, which is a cheaper powder, cheaper material, and making a composite of other with something else, you can improve the performance significantly. What about degradation? We are talking about performance like it should be good, it should be like that, but it should survive as well. So we did testing for up to like 60 hours using these catalyst materials to see how they perform. Even though manganese oxide material started low, it stayed stable, whereas nickel cobalt oxide degraded very quickly. Why we stopped at 60 hours? It is not because of the catalyst material, it was because of the membrane. The membranes we have, they are not stable for longer time at 60 degrees C. They are very stable at 50 degrees C, but at 60, they start to degrade, and their lifetime is around 50 to 60 hours only at that temperature. So what can we make from this simple presentation or simple analysis I have given? Manganese oxide-based catalysts are performing better when they are combined with formed as a composite. You can achieve a current density of 1 ampere centimeter square at 1.78 volt. And there is some loss of catalyst material, but I haven't showed you the result, but I can share it with you later. So we did study with this catalyst what is coming out really. So it is like you have some amount of nickel coming out and you have some amount of platinum leaching out from the system. So, and the resistivity is modifying. So that's what we were observing when we were doing the degradation. Why actually the material is degrading? It is because your catalyst material is leaching out of the system. Okay, so now I will move on to the AEM fuel cell systems. Why we are studying AEM fuel cell system? Because the catalysis reaction are faster in alkaline condition than they are in acidic conditions. You can use non-noble catalyst materials instead of expensive platinum material, like you can use transition metal-based materials, and you don't have to use non-fluorinated membranes. You don't have to use fluorinated membrane. You can use non-fluorinated membranes like LDPE-based, HDPE-based membranes, which are cheaper and easier to manufacture. You don't have to deal with the fluorine group, which is present in Neff-ion, which is the acidic membrane normally used. But the problem with AEM is it is not stable above 50 degrees C because your membrane is not stable. And thus you can't use it. So that's where we are trying to focus on developing new membrane systems, which can survive for 60 or 70 degrees C. We tested the same in electrolyzer cells, and we are doing the same for the fuel cell systems as well. So some of the performance results which we had, so because this was done just for the membrane setup, so we are not using non-precious metal catalyst. We are using the platinum system because we wanted to study the performance of the membrane rather than the catalyst system in this case. So we had different types of membrane. We synthesized PVVC, we synthesized SCBS, as I showed you earlier, the ionomer, we made membrane out of it, or we synthesized different other membranes as well. So you can see the SCBS-based membrane and ionomer performed better in this case compared to the commercial ones which are available in the market. So we had something going in the system. And why this is performing better? Because we have very low resistance compared to the other commercial membranes. So these two, PVBC and SABS, were synthesized in-house. How does it work? Or the values just given there, what are the resistivity values which we observed? How does it perform at 70 degrees Celsius? They are performing okay. You see the commercial one of the commercial did not do much at 70 degrees Celsius. The other is much better, but ours have a much better power at lower voltage compared to the other the membrane. So that's what we are doing. We are trying to synthesize different systems like that. So 70 degrees C, we know there is good performance, and we will be doing some testing on the degradation as well. But before we move there, I wanted to show you some results on how does catalyst layer thickness affect the membranes. So we are using some SCBS and PVVC, which are the in-house. So how do you vary the catalyst layer thickness? You can use a different type of catalyst. Instead of using 20% platinum carbon, you use 40% platinum carbon because you have more platinum and less carbon, so the thickness becomes lower. So you have a thin catalyst layer. So why do you need a thin catalyst layer? Because then the resistance of the catalyst layer is better, so you will have better improvement in the performance. As you can see here clearly, that PVBC thin layer catalyst is performing much better, and SCBS, even though it is a thin layer, it is not performing better because it might be losing water. So that's what we were trying to see, how they are performing. And if you go at 70 degrees C, the thin layer, it's performing better for PVBC, but for normal, it's just gone down, normal thickness, because it is too flooded. You are generating a lot of current, so you are generating a lot of water, and that's why it's getting flooded and it just died down. Whereas if you look at the SCBS, the thin catalyst layer, it dried out of the high temperature. So you can have the drying as well as the flooding at the same time. So that's where water management comes into play. So you have to manage your water properly, that's why you have to think about whether the ionomer or membrane you are using, it is suited for a thin catalyst layer, or is it suited for a thicker catalyst layer? So the resistance values for these materials or these layers are given here. Now, we have the performance, we studied the effect of catalyst layer. What about the degradation? How does these membranes or these systems degrade? So we are comparing SCBS with an ACTA ionomer, which is one of the commercial ionomers. So you see our SCBS is more or less stable at 50 degrees C, whereas ACTA has started to degrade a lot. And you can see clearly the performance degradation after like 50 hours. The performance has degraded, but it is much more stable than the ACTA material. So there is something which is going on, and we have a slightly better system working towards it. So the values of the resistivity before and after the testing. Now, we don't worry about the 50-degree system. We wanted to develop system which is stable for 70 degrees C. So you see, at 70 degree, even though the performance has gone down or slightly slightly lower than 50 degrees C, but the stability is much better compared to the other commercial ionomer. And you can see the system here, like the performance, it is slowly degrading, but it's much better than the commercial ionomer, which has started going down. So it has like punctured. That's why it is starting at 0.5 instead of it starting at around 0.95. So we have a good system going on. Again, the resistivity values given for these two systems. So you saw that I have only showed you result up to 15 hours. That's where I was saying that AEM system is good at lower temperature, but it is not good at 70 degrees Celsius, and that's what we are trying to do. So our membrane died down after like 25 hours, because you see, starting slowly after like 15 hours, the performance started to go down very quickly. Why it happened? Because the membrane has punctured, which we could see from the change in the crossover current. So the crossover current is when you have the leakage of one gas from one system to the other system. So we were measuring the crossover current, and you could see that there is crossover of the gases. So the membrane has punctured during the process, and that's why we were losing a lot of performance. That's why you see the jump from here to here, sudden jump. That is due to the performance change. And you can see the same thing using impedance as well. Like membrane resistivity stayed the similar, but you are losing the performance quickly. Okay. So what you can conclude from there, SCBS, which we have developed, it is better at 70 degrees C compared to previous or commercial ionomers, but it is only stable up to 15 hours. So we are still developing more materials to see if we can make stable membranes and ionomers for longer duration. Yeah. And I wanted to thank some of the funding partners and some collaborators who have worked on this project with me. And thank you for this. And I will be happy to take any questions or you have.
Thank you, Dr. Gaurav. It's been an eye-opening lecture, because you have shown plenty of experiments, what you have done with the results, and then clear analysis. Are you there? I think you.
Yeah, I'm here. Yeah.
Yeah, fine. I think it got stuck. Okay, fine.
Oh, yeah.
So I request the participants to please post your questions, or if you wanted to ask him directly, I can unmute you. I need you people to please ask him the questions. Yeah. I think someone is asking.
So Lakshmi has a question. What are the key benefits of AEM technology compared to traditional PEM? So the main benefit is because in PEM, you are using platinum catalyst, which is one of the most expensive material. And even if you are reading some literature and all, you will see that platinum reserves are very limited. And we are using platinum at a very fast pace. So sooner or later, we are going to run out of platinum. And even though we are trying to recycle some of the platinum, but it's not easy to recycle platinum as well. So that's where you want to look at materials which are more readily available, and we have bulk quantity of it, and which can be easily used. And that's where AEM technology comes, because you can use the simple transition metals which are available in plenty everywhere over the world. So you can use them as catalyst material. That's one of the main benefit.
Ms. Lakshmi, I have unmuted you. if at all you need to have more clarification, you can directly speak. Thank you. Anyone else? Don't worry about your lunch, participants. Just please ask the questions to the speaker. And they're all hungry, maybe.
Yeah,
Uh,
it's breakfast time for me as well.
okay, fine. There is one question from my side.
Yes, yes, please.
I think you mentioned the longer the reaction time, the better the ion exchange characterization.
Yeah.
So could you please shed a bit more light about what exact experiments you have performed and how could you come?
So that is like the reaction time of the synthesis of the material, so of the
Okay.
membrane. So we did synthesis at couple of different time period. So because when you are exposing it to longer time, you are having more linkage of the two materials. But if you expose it even longer, you start forming like cross-linking. So which is not good. If you are cross-linking the polymers, you are getting better mechanical property, but you are losing the ion exchange capacity. So that's why we had to stop it at like 22 hours, because after that we were doing more cross-linking and less of what we wanted.
Yeah, that's true. That's true. Yeah, it's understandable. Yeah. And you said the membrane is the one which restricting you to do the experiments only for 60 hours, is it?
Yeah, because the commercial membranes which we use, they are also not stable at 70 degrees. 50 degrees C, it's very good, but 50 degrees C, you will have a lot of problems because water management is not easy at 50 degrees C. At 70 degrees C, water management is better, but you have drying issues and the membranes are not stable. So the membranes which we tried, they are stable only for like 20 hours, so 30 hours, not more than that. So that's where we are working towards getting more membrane. So there are some membranes which I have not shown here. They are PPO based membranes, which are slightly more stable compared to the SCBS membranes I have shown. So that work was done by one of the PhD student who graduated this year.
Okay.
And it's published. I can share some of the papers later on with you.
Sure, definitely. We would love to see your research work. There is one question from the participant. I think Gopi Krishna. Just one second. You can ask the question to the speaker directly.
The question is, what should be our main area of focus, membrane or catalyst development? I would say membrane has to take a little bit more priority, because if you want to operate the system at slightly higher temperature, there are a lot of catalysts which can still work, even though they may not be great catalysts, but they can work. But the membrane, it's one of the limiting factor which is affecting this thing. That's my personal opinion from what I have researched on. So others may have a different opinion, but yeah.
Lakshmi has another question.
Can you explain the role of catalyst in AEM electrolyzer and fuel cell and recent advancement? So basically, why do you need catalyst? You need catalyst because these reactions, they will not happen without catalyst. They may happen, but the kinetics will be very, very slow, that it's not worth doing. So these catalysts helps improve the kinetics of the system. So one of the major problem in fuel cell or electrolyzer is the oxygen side. That's the troublesome reaction. That's the slowest reaction. That's where, if you see research papers on any catalyst, you will find 90% or more focusing on oxygen side and less on the hydrogen side, because that's the troublesome reaction. So currently everyone is trying to move away from platinum, even if it is by just alloying it with some other material or completely looking at different material by replacing platinum. So that's where alkaline, we are not looking at platinum, we are looking at transition metals, because they are cheaper and easily available. So you are trying to combine them either among themselves, or you are trying to combine them with lanthanides, which are slightly more stable and can impart that performance to that stability to your catalyst materials as well. So we are working on some of those perovskite materials as well currently, but I have not showed you result, because if I try to show all the results, it will be a very, very big lecture and I won't be able to explain everything together. So that's why I have shown only some of the results. Yeah.
Yeah. Anyone else who would like to discuss with the speaker? We still have 5 minutes more. I really want you to be enthusiastic and interactive. And if someone working in this area, they can definitely get in touch with Dr. Gaurav. He'll be more happy to.
Yeah, I will be happy to have any questions if you want. I think Dr. Vishwanath has my email, so you can directly email me as well.
Yeah.
I will be happy.
Seems like there are no more questions. So I think we would end up here. Yeah, I think so. Yeah.
Okay.
Okay, Gaurav. Thank you very much.
Thank you so much for
your
the opportunity. Yeah. Yeah. That's good. It's good to discuss these things among students and staff combined. Yeah.
Yeah. Of course. It's because it helps us also to share our views. We will also understand.
No, that's true. And because of the recent modifications, because we are working towards sustainability, so it's better to do it online so that you can communicate, so you don't have to travel everywhere.
That is true. Yes. Thank you so much. And I think there are still some questions or maybe general appreciations, I guess. So yeah. Fine. Okay. Thank you, sir. Thank you very much, Gaurav.
Thank you.
Hope we meet again in near future.
Yeah, sure.
And anyway, I will be in touch with you through the LinkedIn. Thank you very much.
Okay, yeah. Okay.
And also
thank you.
Teams.
Bye.
Thank you very much. I will share the drive. If at all it's okay for you to share the PPT, your lecture.
I will have to check which portions I can share and which I cannot. So I will get back to you on that.
Sure. Yeah, because some of the participants are asking for the presentations. I said it's up to the speaker, because not all things can be shared.
Yeah, because some of these are published work, so I can easily share that. That's not a problem. But some of this is still ongoing work, so I don't really want to share all the details before it is published. So
yes, understandable.
Yeah. But I can share the publications. That's fine. Yeah,
fine.
Will be easier. Yeah,
that I can share to my participants. Thank you.
Okay.
Thank you very much. Thanks a lot.
Bye.
Thank you very much. Bye. Participants, I'm sharing you the feedback link. Please stay for some time and fill up the feedback. Thank you.